Namashivaya. In this video, we are going to learn few important name reactions involving alkanes, alkenes and alkanes. The first reaction is Wurtz reaction. It is a reaction used for preparing alkanes, especially symmetrical alkanes. We take alkyl halide with sodium in dry ethyl ether medium. This alkyl units combine to give alkanes. In case if we take methyl chloride, two methyl groups couple to give ethane. Instead, if we choose ethyl chloride, we get N-butane as the product. What happens if we take two different alkyl halides as shown here? When we take methyl chloride with ethyl chloride for Wurtz reaction, we get multiple products as listed here. When two methyl groups couple, we get ethane. When two ethyl groups couple, we get N-butane. When cross coupling happens between these two, methyl and ethyl, we get propane. So, ethane and butane, they are symmetrical alkanes. So, symmetrical alkanes mean you can divide them into identical halves. Similarly, I can write this is ethane, this is N-butane. We can divide them into identical halves. If we write propane, we can't do such division here. So, this falls under unsymmetrical alkane. Now, using Wurtz reaction, we can easily synthesize symmetrical alkanes. When we try to prepare unsymmetrical alkanes, what happens? We get mixture of products. So, now when we get mixture of products, we have to separate and purify them. So, separation and purification. So, this basically is a difficult process to do in lab. In practical sense, therefore, Wurtz reaction is not suitable for preparing unsymmetrical alkanes. The key points about this Wurtz reaction are: this reaction must be conducted at a completely dry condition. That is, there should be no moisture present while conducting this reaction. We are taking, you can see the reaction. We are taking metallic sodium for this reaction, and sodium metal reacts violently with water. Therefore, water must be avoided at all cost. This, as we have already seen, is very much suitable for preparing symmetrical alkanes, and this reaction gives the best results with primary alkyl halides. When we take different alkyl halides, alkyl iodides and bromides, they react better than alkyl chlorides under Wurtz reaction conditions. This reaction is not suitable for tertiary alkyl halides. In addition to getting a coupling product, sometimes we get elimination products as well as side products. Moving on to the next reaction, Frankland reaction. The reactant and the product, they are the same as in the case of Wurtz reaction. The thing that differs is the reagent. In Wurtz reaction, we used metal sodium or metallic sodium. Here we use zinc metal for Frankland reaction. We start with alkyl halides. We allow it to react with zinc metal. We get alkane as the final product. Zinc halide will be a byproduct. Example, when we take methyl chloride, we get ethane. When we take ethyl bromide, we take N-butane as products. The next reaction is Kolbe synthesis. It's a very ideal synthetic strategy for preparing higher alkanes and unsymmetrical alkanes. This synthesis takes place in multiple steps, and we see how it happens now. And the overall reaction can generally be given as alkyl halide in presence of metal lithium, dry ethyl ether and copper halide giving alkanes. We will see what is the synthetic strategy involved with the first step will be the formation of alkyl lithium. Say for example, I take methyl chloride as Rx. This reacts with lithium. So one lithium will go with methyl, the other lithium goes with chloride. So methyl lithium and lithium chloride will be formed in the first step. So this methyl lithium, what is formed in the first step, reacts with copper chloride I am taking for the reaction, and this produces a compound called Gilman reagent, and this Gilman reagent is lithium dimethyl cuprate. I'll repeat, lithium dimethyl cuprate. So this is called as Gilman reagent along with lithium chloride. In the third step, the real coupling happens. So based on the requirement I have for my alkane, I have to choose a particular alkyl halide. Now along with this Gilman reagent that is formed in the second step, I add an alkyl halide. So in case if I take methyl chloride, I will be getting ethane here. If I take ethyl chloride as shown here, one of the methyl groups from this Gilman reagent goes and couples with the Rx I am taking, the R of the Rx, producing propane. Okay, so based on the alkyl group I am having in the alkyl halide, I would get different alkane in the product. Okay, along with this I get these two as products, methyl copper and lithium chloride. The key points about this reaction is the Korehouse synthetic strategy gives unsymmetrical alkanes, especially with better control in comparison to the Wurtz reaction. It also produces less side products, and it's highly useful in synthesizing long chain alkanes. What's next? Kolbe's electrolysis. Here we use the salts of carboxylic acids and we allow it to undergo electrolysis to get alkanes as products. So, for example, if we take sodium acetate, 2 methyl units from the salt coupled to give ethane as the product. This COO moiety, it escapes as CO2, and hydrogen also is liberated from the water we use for the electrolytic process. Since there is a removal of CO2 from the original reactant we have taken, this is a decarboxylation reaction by nature. We see how it happens. As we know already, for an electrolytic process we need to have an anode and a cathode. At anode normally oxidation takes place. Oxidation of the carboxylate ion takes place to give methyl radical, and CO2 escapes along with the production of electron. Now at cathode, the water we have taken for the electrolysis process undergoes a reduction to produce hydrogen and hydroxyl. So by combining and balancing the reaction, we get the final reaction as shown here. We can see clearly the 2 methyl radical what we had here, this couple to give ethane, and COO minus escapes as CO2, and hydrogen's liberation from this unit along with the production of hydroxyl ions. So in this reaction we can prepare symmetrical alkanes with even number of carbon atoms. We cannot get odd number of carbon atoms in our product in this case, since it's a coupling reaction of the radicals. Only one carbon atom less than the parent acid we have taken for the reaction. In case if we take mixture of salts, obviously we will be getting mixture of alkanes in the product. This method is not suitable for preparing unsymmetrical alkanes.